Hello everyone. In this video clip, I'm going to go over two sections, 2.5 and 2.6. In 2.5, I'm going to give you the definition of continuity, a more formal definition of continuity rather than what you've seen in college algebra and in pre-calc class. And then after that, on section 2.6, I want to show you some application or some use or some extension of understanding about the limit when things go to infinity, and you guys going to see the asymptote of the graph. Okay, so let's start with section 2.5 about continuity. So you guys have heard a lot something say a function f of x is continuous. Okay, but more precisely, whenever you say f of x is continuous, we have to say it's at a point. Continuous, say at a point x equal to a. So continue at the point A right here. And more than that, moreover, that point A got to be on the domain, okay? At the point x equal to a on the domain, on this domain. Another word, we cannot talk about continuity if the point is not on the domain. So whenever you have a function, the very first thing that you guys have to care about is the domain of that function, okay? So when you talk about continuity of function, or if a function is continuous at a point, that point gotta be on the domain of that function. That is the first condition that you have to care about. So f of x is continuous at a point x equal to a on its domain if the following condition happens. Okay, the limit of f of x when x approaches a equal to L, and f of a is equal to L as well. Or, in short, we can write this way, equal to L equal to f of a. So let me write this way already, I don't have to erase it. Okay, so what is that all about? It's saying what? First of all, you have the point A right here, x equal to a is on the domain of the function. And it's on domain, and then what? If you can move to the left and to the right a little, the entire little piece of the curve of the function gonna be on the domain as well. Because when you have any value of x is close to it and approaches a from either the left or the right, the functions have all the values on that interval. Okay? So in short, it's like intuitively you can say what? It's continuous at a point means what? You can have a little short curve that move to left or right from that point. And if that happens, we say what? F of x is continuous at the point x equal to a. And that point got to be on the domain. And mathematically, how do you check if a function is continuous at a point? You do two things for me. Number one, you calculate the limit of the function when x approaches a. Okay? And then you plug in a to the function. F of a equal to L. That those two numbers agree with each other, equal to the same value. And you say what? Yes, the function is continuous at x equal to a. Alright, so this is the definition of continuity, and pretty important. Stick with the definition, guys. Try to use less of your intuition and be more on the definitions, because sometimes, if not many times, your intuition may betray you, may be opposite of what you see in the definition. Okay, so let me show you a couple of examples of, or counter example of continuous function or not continuous function. Example. This function right here, okay? And this is my point. This is 3. And this is 5. It's one curve. Alright? And I claim this is a function that's continuous at x equal to 3. It's continuous at x equal to 3. Because when x is approaches 3, anywhere x right here getting to 3, and f of x is getting close to 5. And moreover, until s3, because the limit of f of x when x approaches 3 equal to 5, and f of 3 is also equal to 5. Okay? Is that point on the domain? Yes. So far, so good. How about another example? Or counter example. If I give you this. This is my function. Now that I have a hole right here, and this is a point right here, and this is 3 right here, this is 5 right here. I have the limit of f of x when x approaches 3 is equal to 5. And say when x getting close to 3, then the function is getting close to 5. However, when this is say 2, when I plug in f of 3, I got f of 3 is equal to 2. Those two numbers are the same. Okay? Limit is 5, but that specific value at the point 3 is just 2. When x is close to 3, f of x getting closer to 5. So this is what? 5.1, 5.01, 5.00 all the way to 5. X getting closer to 2, to 3 I mean, then what? F of x getting closer to 5 from the lowest of 4.9, 4.999 get to 5. However, when you plug in the exact value for x equal to 3, f of x turned out to be equal to 2. This one right here, and it's not continuous at x equal to 3 because the two values is not agree with each other, not the same. Okay? What about this one? Okay? So this is 7. And I claim that in this example right here, the function is not continuous at x equal to 3 as well. Why? Because limit f of x when x approaches 3 does not exist. Why it doesn't exist? Because the limit x approaches 3 from the left is equal to 5. But the limit x approaches 3 from the right is equal to 7. Okay? Limit f of x, x go to 3 from the left is equal to 5. Limit f of x, x go to 3 from the right is equal to 7. It doesn't have the limit. Now I don't even care about the value of the function at all. It has two things to have continuity, right? The limit equal to the value and the function equal to the same value. In this one right here, it doesn't even have a limit. So for sure it's not continuous. And don't forget to check if the point 3 is under domain. In this case, is that under domain? Yes, that's the first thing. We said the f of 3 equal to 5, right? So the point x equal to 3 is under domain. So that's good, but the function is not continuous. Not continuous. Okay? Now, let me give you another example that a lot of people may get confused. So, it's going to bring back everything that I mentioned today to get to the example and make sure that you guys understand the whole thing about this. Take a look at the problem. How about this? F of x equal to, say, 1 over x minus 2 is the hyperbola. Okay. See? It has the vertical asymptote right here at x equal to 2. This is the origin. And this is the y-axis, the x-axis. The graph looks like this. Okay. And this is usually what I show students in class, face-to-face class. I say, well, I show the graph of this function. This is the exact graph of the function. And I ask students, is that function continuous or not? And I bet many students, quite a number of students, will say this function is not continuous. And I claim that that answer is not correct. The correct answer is yes, this function is continuous. And I usually ask why you say it's not continuous, because see what you have two pieces of the graph. When you draw it one curve, you have to lift up the marker and you draw another curve. That's why it's not continuous. Intuitive, usually people say it that way, but I claim this function is continuous. Why is it? First of all, you have to talk about the domain of that function. Okay, so what is the domain of that thing? All real numbers except x equal to 2. So the domain is what? Negative infinity to 2 union 2 from infinity. Okay? It means what? Number 2 is not on the domain. Alright? X equal to 2, we are not allowed to plug in x equal to 2 into the function. So 2 is not under the domain. In other words, we can talk about any value for the domain except for 2. Okay. So if they ask you continuity, they have to specify the point. Is that continuous? Is that continuous at x equal to 2? The question is invalid. It is because 2 is not under the domain, so we cannot ask about continuity at x equal to 2. We have to talk about continuity at somewhere else. And of course, when you ask about continuity at any other point, say 2, 3, not 2, 3, 4, 5, 2.5, any other points, right? You can move a little bit left, a little bit right. So yes, the function is really being continuous at every single point on its domain of the function. Yes. Okay? Now this one really is continuous. It's continuous because it is continuous at every single point on the domain. And again, since 2 is not on the domain, there's no right for us to plug in x equal to 2 into that function. So we're not allowed to talk about continuity at 2. Therefore, the function is continuous. And there's another little signal that you can see. You have 2 intervals for the domain. And on each interval, you are drawing the curve with just one curve without lifting up the marker. So this interval from negative infinity to 2, you have one curve continuous on that interval, right? And then 2 to infinity, there is continuous as well because you draw it with one curve. Really. So one more time, for continuity, we have to look at the domain of the function first. And whenever we talk about continuity, first of all, we talk about continuity at a point on the domain. And in this particular example right here, even though there are 2 pieces of the graph function, 2 curves for the graph of the function, but the function is still continuous because for any point on its domain, anything except for 2, you can find the limit, and the limit is equal to the point. Say the point right here, say 3, right? The limit x approaches 3 is 1 over 3 x minus 2, which is 3 minus 2, right? It's 1 over 3 minus 2 is equal to 1. And then f of 3 is equal to 1 over 3 minus 2 is still 1. See? The limit from the left and the limit from the right, because when limit, you don't care about the whole thing. When any x goes to 3, and then you get to 3, and then equal to f of 3, which is 1. So yes, the limit does exist, and the function at 3 equal to 1 as well. Same number. Yes, by definition, the function is continuous, x equal to 3. What about x equal to, say, 1.5, somewhere right here? Yeah, 1.5. Oh boy, the graph is down here, right? 1.5 is down here. Then what? Limit from the left, limit from the right is get to that point, and 1.5 minus 2 is negative 0.5. 1 over negative 0.5. This is negative 2. See? The same. So it is continuous everywhere on the domain. Okay? Careful. Now, let me change the story a little. What if I have a function this way? I'm going to keep the same graph. F of x equal to 1 over x minus 2 if x is not equal to 2. And then f of x is equal to 3 if x equal to 2. So this is my function. Let me use red color to indicate the singleton. X equal to 2 right here, and I have a point 3 up here. This is a point on the graph. Okay? Now, what is the domain of the new graph right here? We have what? Negative infinity all the way to something that less than 2. And then we have the 2 on the domain, right? F. We plug in 2, you got 3 out. Right? X equal to 2, 3 out. And we have something bigger than 2 in here. Okay. So the domain now is what? Negative infinity to positive infinity. And I declare that this particular example, if you add one more point in here, this function now is not continuous. Why is it? Well, not continuous at x equal to 2. Okay? It's not continuous at x equal to 2. Why is it? You take the limit of f of x. When x approaches 2, what happened? When x approaches 2 from the right, the function goes to infinity. X approaches 2 from the left, the function goes to negative infinity. And we can do it now because 2 now is on the domain. X equal to 2 is on the domain. Unlike the previous example, we don't have this line right here because we don't have x equal to 2 on the domain. So there's no right for us to talk about the point x equal to 2. It's not on the domain. Now we okay because the x is on the domain. X equal to 2 is undefined, does not exist, because the limit of f of x, when x go to 2 from the right, is equal to positive infinity, whereas the limit of f of x go to 2 from the left equal to negative infinity, the limit doesn't exist, and you don't have continuity, even though f of 2 is equal to 3. We do have this, but that is not equal to 3. So it's not continuous. Okay? So please be very, very careful when we talk about continuity, not just using our intuition and what, oh, I'm looking at the graph and I see that it's drawn with 2 separate curves, so it's not continuous. Okay? Without that point right here, the function is actually continuous, even though you're drawn with 2 curves, because the domain is negative infinity to 2 parentheses and then 2 to infinity parentheses. We're not allowed to talk about value 2 for x because it's not on the domain. The second example that I gave you right here, I just simply add another point into the graph. Now that the domain is what? From negative infinity all the way to positive infinity. Include every single point. Okay? 2 is on the domain. I plug in 2, I have the limit x approaches 2 is not defined, so f2 is equal to 3, not the same. So the function is not continuous at x equal to 2. Okay? It could be continuous. It is continuous at every other point except for x equal to 2. If you are having that point on the graph. Okay? Hopefully that clarify your understanding, help you to understand the definition of continuity a bit better. Now, after having continuity, let me just go back to the limit and talk more. I think I mentioned this already last time on the previous video clips, but it's officially on 2.6, so let me show you some limits at infinity, and now I'm allowed to use the epsilon delta definition to talk about, okay, limit at infinity. We have several cases. I think last time I gave you this. Remember actually the other example works. When x goes to infinity, say this is a line, say 5 right here, right? If you have a graph like this, this is f of x, okay, L equal to 5. This is 5 right here. X-axis. It's a function. If you have what? Limit of f of x, x goes to infinity, the limit at infinity, x goes to infinity, equal to 5. And what does it mean by this? When x getting bigger and bigger all the way to infinity, what happened to the function? It's getting closer and closer to 5 and 9 kilometers. That is a signal to tell people that what? The graph will have a horizontal asymptote at x equal to 5. And similarly, you can talk about the other side right here. Limit f of x, when x goes to negative infinity, also equal to 5, but now what? A little bit less than 5. And that's also indicated we have the horizontal asymptote at y equal to 5. Okay. Or limit x go to negative infinity of f of x equal to 5 as well. Those, either one of those indicated what? The horizontal asymptote at y equal to 5. Of course, 5 here is just a random number that I put on the example. It could be any other constant. Okay? And in terms of the epsilon delta, let's go to infinity. People can write this way. Limit f of x, x go to infinity, equal to, say, number L. We say it this way. For any let the m really big, okay, m here, any value m, go to infinity. For any m really big, they exist at epsilon greater than 0, such that when x is greater than m, then f of x minus L is less than epsilon. Okay, we write this already, but let me just explain to you. This means what? Whenever you choose, doesn't matter how big the m is, I can always find the epsilon. Now what? The epsilon is the distance between the curve and fiber, I can always find a positive number. There's a gap between those two, such that when x is really far away from the origin, then the distance from the function to the line 5 right here is smaller than epsilon. Okay. Oh, I wrote it backwards. Sorry, guys. For any epsilon positive, there exists a bigger m. Okay. Correct this for me, please. Doesn't matter how small you have for the distance. I can always find the m. The other ways of saying is right, but we got it right this way. Okay. Whenever you choose an m that's very big, then what? The function is getting close to epsilon, and this is the way to write it. Fix that for me. Okay. It's incorrect to write the other way around. It will be the right way. And of course, if x goes to negative infinity, we're going to write this way. Limit f of x equal to L when x go to negative infinity. For any epsilon positive, there exists so m is positive, such that if x is less than negative m, now m is positive, but negative m is going to be the other side, right? Even smaller than that, then f of x minus L is less than epsilon. Same idea because we talk about negative infinity, so less than negative m for the other side. Okay. Now we have this kind of infinity. Say you have a graph like this. What? When x go to infinity, y go to infinity as well. Or maybe the other way. Okay? X go to negative infinity, y to go to negative infinity. I'll just give you one example, one definition of x go to infinity, y go to infinity, and the other way. The other things you can figure out by yourself. How do you write the definition for limit f of x? When x approaches infinity, x getting bigger, y getting bigger. Go up forever. Okay? So whenever you have a bigger m, then you have a bigger m for y value. How do you write this? For any n positive, okay, this is m right here, n right here. Let me double check on this, make sure that I write it right. For any n positive, you can always find the bigger m, yeah, positive, such that when x is bigger than m, yeah, x is bigger than m, then f of x is bigger than n. That's it. And of course, the other way around, what? X is less than negative m, and f of x is less than negative n. So x goes to negative infinity, f of x goes to negative infinity. Okay? You just change the sign, one of those. You have no definition. Okay. The book did mention about the vertical asymptote, but I briefly mentioned the vertical asymptote on the previous video clip. Let me go back to here one more time. Say I have the vertical asymptote, let's say x equal to 2 right here. And how do we apply the limit at infinity to find the vertical asymptote? And this is our function, okay? F of x. Limit f of x. Look at the graph, guys. Limit of f of x when x approaches 2 from the right. So 2 is right here, okay? Keep in mind, I never say that x equal to 2. I'm saying x is getting closer to 2. And from this sign is from the right. Means what? X is a little bit bigger than 2 and it's going down to 2. Okay? What happens when x approaches 2 from the right? The function is going to infinity. Okay? Similarly, limit f of x. X approaches 2 from the left. The function goes to negative infinity. Either one of those two limit indicates that we have the vertical asymptote. at x equal to 2. You see, when x goes to 2, go to infinity, negative 2. I'm sorry, still go to 2 negative, not negative 2. 2 minus. Then the function go to negative infinity. And I claim that you only need one of those two conditions to say that the graph will have a vertical asymptote at x equal to 2. Okay, and of course you can write the epsilon delta definition for this as well. The same thing as what we wrote before. This is the end of this video clip today. Thank you so much for watching, guys. Have a good day.